This conference will now be recorded.
All right, you should be good to go. Okay, look, your screen looks good.
Okay, thanks, Rich. Hopefully everyone can hear the audio and has the screen visible. As Rich mentioned, today I'm going to be talking about the Pangeo project and how we're using it with NASA's satellite observation data. And I'll just give some backgrounds, probably about half an hour of slides describing the project and how and my involvement in it, and then also show a demo towards the end. So I am a postdoctoral fellow at the eScience Institute at the University of Washington. And I'm going to hopefully, advance through these slides. Okay, there we go. So the Pangeo project, as Rich mentioned, has been talked about quite a lot in these ESIP webinars. So I have some links in these slides, and if you look in the chat, there's also a link to the slides on Google Drive. A lot of links throughout this presentation. I'm just hoping that people can use those to refer back to the various things I'm going to talk about. But what is Pangeo? Pangeo is a community platform for big data geoscience. It's many things, and it's not exactly a dedicated software platform. But you can go through these websites, GitHub pages, blogs to really find out more. I highly recommend looking at the Tech Dive videos that have been recorded talking about the project. There's sort of the first of a series by Ryan Abernethy at Columbia and Matt Rocklin now at NVIDIA. It was recorded about a year ago. So this Pangeo project got started a number of years back as an NSF EarthCube project, and there are many groups kind of contributing to this effort and some different funding agencies behind the scenes. I started getting involved in this project when putting together a NASA application for their Access program, and the motivation for doing this was basically this chart down on the bottom left of this slide. This is a chart showing NASA's predicted archive growth over the next several years. And you can see we're just dealing with a tremendous growth in the size of NASA's archive. On the right side is a similar plot showing climate modeling archive growth. And so just throughout the geosciences, people are starting to grapple with archives that they want to access and process for various scientific use cases, but are struggling with just because of the data volumes. So we have a NASA Access project that I mentioned that's now underway. It started basically in September of last year. So it's a 2-year project, and the main goal is really what's stated on this slide: to facilitate the geoscience community's transition into cloud computing by building on top of this Pangeo ecosystem that's been established over the last several years. And this is a team effort. I'm sharing this work today, but really there are many people involved. So this collection here is everyone that was involved in putting together this grant to NASA to try and advocate for using this system of tools. And we have some pretty specific goals in this project. So that main overarching goal is at a very high level, but we also have these specific aims. And again, if some of these terms don't make sense, I'll be getting into a bit more detail in the next slides here. But first and foremost, we are trying to deploy a cloud-based analysis system for the community to use. So we want this to be open to folks logging in that have some sort of scientific use case where they need some scalable computational ability. We're trying to integrate existing NASA data discovery tools with data access. So there I'm referring to NASA's Common Metadata Repository and their system for Earth data search, if those of you are familiar with that. Also, we want to create a cloud-optimized framework for analysis of these large remote archives. So we need tools that allow us to scale our computations, whether we're working with a single image or we want to look over all the images for a given region, say all Landsat data over Washington State. We also have some pretty specific scientific use cases using various satellites, GRACE, Sentinel-1, also hydrologic modeling datasets. And we're also focusing on upcoming sensors from NASA, such as the SWAT mission and the NISAR mission. So again, these links are mainly for referring back to, but you can learn a lot more about this project by visiting these links later on. We've got a blog post describing the project, also more information about the funding, the proposal call, and a nice summary of our project. So speaking of these scientific use cases, I got interested in this Pangeo project because I was starting to work with very large archives of radar imagery. So the figure here on the right is showing Sentinel-1. This is synthetic aperture radar data covering the Pacific Northwest. This is a data set that's been available to the public since 2014, and it's really a huge kind of revolution in the field of radar, especially applied to earth science. It's the first time we've had a publicly available archive and a global monitoring mode for radar acquisitions. So it's a tremendous resource. There are lots of interesting applications, such as trying to put together stacks of radar data to look for slow slip earthquake displacements, monitoring slow-moving landslides, volcano deformation, a lot of applications to tectonic hazards. But there's just too much data processing to keep up with. So this map on the right is just showing the availability, the number of acquisitions as a heat map in the Pacific Northwest. And there are over 500 acquisitions. And if you start combining these acquisitions to interferometry, you're accumulating terabytes of data in order to process it all systematically. So this is the current proxy for NASA's upcoming NISAR mission, which will be launching in 2022. And a lot of use cases we have are using existing data sets to demonstrate how processing on the cloud can be effective for upcoming missions from NASA. We also have, I mentioned GRACE as another data set that is being used. And so the HiMap project, there's a link at the top of the slide here from where this is coming from. But this is an effort to compile many data sets over high mountain Asia. That's what the acronym HiMap stands for. And again, it's dealing with terabytes of data, multiple groups doing separate analysis with satellites such as GRACE, and then using different land hydrology models and wanting to combine those data sets and do joint analysis. So this is another important use case for the tooling we're developing. So I'm going to kind of go into these individual kind of more specific goals through the next part of this presentation and just kind of describe where we're at with the project. So first, we wanted to deploy a cloud-based infrastructure for community use. We currently have a prototype of that on the Amazon Web Services system. I should say there's a focus on this project for Amazon Web Services because NASA's indicated that that's where the NASA archive will be stored in the future. But many of the tools we're developing are designed to be transferable between commercial clouds. So a lot of what I'll show today is on Google Cloud. And this is our first effort to transfer many technologies that have been first deployed on Google Cloud to Amazon Web Services. So,
hey, Scott, I might mention there that URL that you gave there is a whitelisted URL, so it's not completely open to the public. But
right. Yep. Good point. As I mentioned, the design currently is to kind of make these available to people exploring specific scientific use cases. And so many of these first deployments are whitelisted access, but there are ways which I'll show throughout the presentation to launch this sort of analysis for your own work very easily.
Great.
So, yep. So this schematic kind of represents where we think we're at today as far as how scientists work with NASA data. For the most part, there's this interaction with the DACs, and you're operating on your local computer and requesting data from a specific DAC, which, if that acronym is not familiar to people on the call, it's a data archiving center, distributed archiving center by NASA. And there's a bottleneck there because there's a lot of duplication of data downloading, and this is becoming especially inconvenient as these archives grow and the image formats grow in size. So on the right is the envisioned system that we're advocating for via the Pangeo project, where everything is happening on the cloud, but the interaction is still through some local workstation. So it seems like you're just working locally, but in fact, you're attached to a vast amount of computational resources behind the scenes. And this is all being kind of integrated with the Jupyter project and various Python programming tools. So this is just at a schematic level, and I'll get into some more specifics since it's a tech dive. This is a screenshot of what that interface looks like to the user, and I'll go through a live demo of this later on. But if you have not used a Jupyter Lab interface before, it's running a notebook in your web browser. So you're running Python code. The code is being executed on machines that are on a cloud provider. So that could be Amazon, that could be Google. You can see tabs in the upper right specifying Dask workers, Dask progress. Dask is what's being used to manage a network of distributed computers. So when you run computations, it's not running on a single machine, but actually being parallelized for you and run on various machines. So this is a very interactive environment. It's browser-based, so there's a lot of browser-like functionality of streaming images and doing interactive plotting, which can be shared via links. So it's a very nice interface for computation. And we think there are a lot of benefits to this style of computing. You have instant access to launching this machinery. So this stood out for me recently with, for example, the shutdown of NASA's Pleiades system, where researchers were locked out for a while due to the shutdown, and hopefully that is remedied for next week. But the instant access is a nice feature for running batch jobs that otherwise you may have to queue up for or wait for. You have a centralized repository where teams can access shared datasets. So the key feature here is that you're moving computation and running of scripts to wherever the data is. You're not duplicating data archives and moving them back and forth across networks. It's a secure location for team members. As Rich mentioned earlier, that's one of the advantages of this whitelist system. It's very easy for people to log in, just as you would to your Google account, to access this, this type of computation. And that fourth point I already mentioned, really. We're trying to avoid shifting data at all costs, moving data. And it's a pretty flexible architecture, really. You have some sort of distributed storage that's necessary. So this will be cloud storage buckets like AWS S3, or Google Cloud has a similar system. And we're imagining that this is where these archives of data are stored. The computational interface, focusing on the cloud here, but we've also deployed some of this architecture on HPC systems, high performance computing systems. And Kubernetes is the orchestration that's behind the scenes launching a parallel system for computing. And Dask is a Python package that knows how to talk to Kubernetes and farm out your computations to the various computers that are available to Dask. Jupyter is this interface, as I mentioned before. And Xarray is another Python package that is very intuitive for working with imagery data sets. So this is just another kind of high-level schematic of how this works. And we're really hopeful that this is going to make people happy about processing data again and remove the frustration of waiting for downloads in particular. So there are two ways to launch this architecture. There are persistent deployments specified on the left. So that link that we had up before to the ESIP prototype on AWS, as we mentioned again, that is a whitelist access deployment. It's designed to be permanent. This sort of deployment is good for a domain-specific research team. So if you want to set up your own system just for a research team, you can go about it that way. And whoever's deploying that system pays all the associated computing costs. There's also a very convenient tool that we, and Joe Hammond in particular, as part
Scott, I lost your audio.
looks like we may have lost audio.
Oh, okay, you're back.
Yeah. Okay, sorry.
Can you repeat that? Can you repeat that last slide?
Yeah, I'll go back.
Just the
Discussing.
well, I guess starting from well, yeah, maybe just repeat this slide.
Okay, I'll go back over this. Sorry about losing audio. So
well, we got to binder. Actually, we got to binder.
Okay, all right.
Start with binder, maybe.
Yeah, I'll go. Okay, I'll go over it one more time. So this two styles of deploying this computational architecture kind of outlined here. I'll just repeat what I said about the binder in case people lost the audio. It's a mechanism for automating launching this computational infrastructure sort of with a one-click interface. So it's very good for launching demo and testing and just trying things out. Storage is not persistent on these systems, so you can't use it as like a permanent file system, but it's very helpful for educational use. Okay, so that's the overview, high-level overview of that computational infrastructure. And the second kind of aspect of this project is facilitating data discovery on the cloud. So I'll talk a bit more about that. So NASA currently has a great system called the Common Metadata Repository. And so that is an effort to consolidate metadata across the distributed archives so that you can search in a single place. And so NASA has an Earth Data Search tool that makes that very convenient and currently gives you links to the distributed archive centers for download. One of the disadvantages currently is that that system still points you to large files that may be compressed in zip formats and whatnot. So you still have to download entire files from the DAX to work with the data. So we'll talk a little bit in these next slides about how that might change when data is actually stored in cloud storage. So the theme of this presentation, the focus earlier on, was a cloud native approach to processing the Earth observation data. And this slide here is kind of thoughts on what that means, that term. And I'll just run through it because I think it's pretty important to clarify what this means. So I would say it means that discovering imagery is very easy as when it's stored on the cloud. This is mainly because imagery can be accessed via URLs. You can access image subsets instead of entire files. So we're no longer downloading 1 gigabyte multi-band files, but you can get a single band, and furthermore, you should be able to access a subset of any given band. You want to be able to run algorithms where imagery is stored and easily disseminate results of whatever algorithm you're running. Again, if it's images via URL. So it's starting to think about, instead of files on a local hard drive, everything is referenced by URL. Also, we want to be able to scale analysis. So regional or global scope to any sort of scientific question you're asking is now possible. And any system should ideally be deployable to any cloud provider. Also, things should be secure and costs ultimately comparable to what you're doing locally. So if you're running on a big server in your lab, we're trying to not develop tools that are fancy and especially expensive, but actually just comparable to whatever workflows we're used to running. So what's the current state of Earth observation data on the cloud? People may be familiar with some of these programs. Earth on AWS is a compilation of Earth observation datasets that's pretty well defined on Amazon Web Services. Google Cloud has a similar program. Here I've just pointed towards Sentinel data, just some screenshots from their web pages. So this data is already there to some degree, but it's not fully there. So I think it's important to recognize that what is currently on the cloud is generally subsets of data that's managed by a third party rather than the data provider. So there are some examples of NASA data currently there. NASA Next program has put up some MODIS data on AWS, but you'll see, as you dig into it, it's not necessarily all MODIS data. If you go to Earth Data Search and by the DAX, this is far from that level of archive. It's updated infrequently, and it tends to be just maybe a single MODIS product. And when data is stored on AWS, there are a variety of variables to consider. So this is a table that we've put together recently showing what data is there currently for Earth observation in particular, what region it is stored in. So these commercial cloud providers are broken down into different regions where basically your data center is. And so you can see here that some of this data is stored in the US West data center, other in the East, other data sets in Europe. And also the formats vary quite a lot today.
So Scott,
Mm-hmm.
I've heard many people go around saying that, everybody's agreed to put imagery data on the cloud and, and cloud optimized geotiff, but I guess that is sort of not, maybe people have agreed, but it certainly doesn't seem to be too often used, at least with this data set, huh?
Yeah, I think it's certainly still being fleshed out, right? Now is the time that people are discussing how is this transition actually going to happen, and the data format is certainly something that's being talked about a lot, but there's certainly no consensus right now. And I'll talk a little bit more about why that is in these next slides, but it's a good transition because Rich just mentioned this cloud optimized geotiff format. What is a cloud optimized geotiff? It's very similar to a standard geotiff. In fact, it works just the same with any legacy GIS program like QGIS. The kind of new aspect of it is just having a sequence within that file. So it's basically a clear specification of having the metadata in front and the data stored intelligently after the metadata in the image file. It's a format that also allows for HTTP range requests. And so why that's important is because, as I've mentioned, as you're storing these files on cloud buckets, effectively they're now indexed as URLs rather than files. So when you access them, you're accessing them via HTTP calls. It's effectively living on a server. And so when it allows for range requests, you can say, I want just a small subset of the file rather than the entire thing. So you could store a 10,000 by 10,000 image, but only pull 100 by 100 pixels efficiently. It's not the only format out there that's amenable for this kind of access. So on the right here is, as I mentioned, InSAR. And similarly, it allows for just more convenient, efficient access on cloud storage. And it's a straightforward conversion between HDF or NetCDF files and ZAR. So as we just heard earlier, Rich was bringing up, there doesn't seem to be a consensus on the format as things are moving to cloud storage. that's partly because of requirements by the archiving centers. So for NASA right now, currently NetCDF and HDF are the only approved long-term storage formats. So anything that's put on the cloud has to be a derivative of the long-term storage format. So it could be NetCDF, and then any derivative projects would be a duplication of that permanent archive. For example, translating to a cloud-optimized geotiff could be done as a service. And one of the groups involved in the NASA project is Element 84, who's put together a really neat demonstration of how that might work for the GOES satellite imagery. So the link for that at the bottom. And many of the cloud datasets are currently managed by third-party providers right now. So yeah, I would say there definitely is no consensus on formats yet, but it's certainly being explored by many groups.
Scott?
Yep.
On this aspect of only approved archive records are types are NetCDF and HDF. If Unidata, I guess Unidata is working on making XAR a backend to NetCDF, would that mean then that you could write your data in XAR or no? Because is it about, I guess is it about the library, or is it about actually, I guess it's probably about how it actually sits on disk. Is that right?
Yeah, I think you just need a set of approved international standards. So if it is a new version of NetCDF, our understanding is that it will still have to go through a process of kind of standards approval to be qualified for long-term archiving. So it would have to be a new, I'm assuming like a new standardized NetCDF version 5 or whatever before it starts being used for long-term archiving.
Right. Okay. Thanks.
Mm-hmm. Okay, and so we've talked a bit about formats there, but the other aspect you might notice as you start to explore these data sets on the cloud is that it's not necessarily easy to find what you're looking for. So one approach to putting data on the cloud is just moving all the files directly into cloud storage and leaving them there. But navigation of that archive is difficult. So one of the great aspects of the NASA Distributed Archive Centers is they have dedicated servers that help you search the data based on bounding boxes or time periods, et cetera. And if you have these data sets on cloud storage, you need some sort of accompanying metadata and search system to go with them. So there's a lot of progress being made right now on what are called spatiotemporal asset catalogs, and this is basically a standardized JSON metadata format for those files stored on the images stored on cloud storage. And I've got some examples of what that is through the links over here. And then built on top of some sort of simple standardized metadata are tools to do searching based on bounding boxes, etc. So there's some great tools that have been developed just in the last months related to discovery of data sets on AWS in particular. And I'll just mention, I think this is a really neat project that's sort of bringing these two concepts together, these spatiotemporal asset catalogs and the cloud optimized geotiff. If you have imagery stored with those two things, if you have that format and the accompanying metadata, it's very easy to build web-based tools on top of that. So here's a great project to browse the Landsat catalog, for example, now on AWS, that's very interactive, and any links that you copy from this web browser, you can share with others. It'll take them directly to the images, and you can browse full resolution images that are tiled on the fly rather than just static thumbnails. It's very neat. And one of the main like motivations behind this metadata system is that it will be indexable via standard Google search. And so I'm not as plugged into that effort, but kind of the long-term vision is that you can simply type Landsat over Washington State, and theoretically, as a Google search, that will retrieve the image tiles that you're interested in. So something to keep in mind is the long-term outlook. Okay, so currently I've just explained some of the technologies we're exploring as part of this project, but what we'd like to do is enable NASA CMR search to utilize some of the tooling being built around the cloud storage. And so a key first step is getting some of that data from the DAX onto web storage, and that's a work in progress. But we think that there's a clear pathway towards using these stack catalogs on top of the other existing standard metadata formats that exist at NASA in order to have more convenient access for cloud analysis. Intake, which I didn't mention in the previous slides, is a to Python, and there was a great ESIP seminar recently discussing that in detail, so I won't really go in detail today. Okay, so finally, now that we've found some data on the cloud and we want to run our analysis with it, there's a combination really of Python packages that enable efficient scalable workflows. And so these are Dask, Xarray, Raster.io, Intake, and PyViz. And I've sort of identified here what exactly they're used for. And I'll just mention too that this is an opinionated list of programs, but there's no reason why you couldn't put different Python packages into this system. So I'll show a demo now that we've talked about some of these tools. There's a list of demos here on this slide, and these are demos that have been put together with the binder tool that I mentioned earlier, and it's really to launch tutorials. So if you click on the link on that webpage for the ESIP Tech Dive materials, you'll see there's a Launch Pangeo Binder button at the bottom, and anyone can click that. In fact, I encourage you to now. One of the beauties of this system is that people can run this code in parallel and not interfere with each other. So this is going to launch a system that I will demonstrate here. I already have one of these pages open, but you should, when you click that button, you launch this browser interface that looks like my screen here, and you will be in a home directory with this welcome page. There's some instructions on these. Sorry, these instructions might be a little dated because they're actually for our AGU tutorial. So in the link in the slides, there's a link to the AGU demo, which has some of these getting started in other notebooks. But the one I'm going to show today is from this ESIP Tech Dive launch binder. So you get.
So that's Scott. That's the first. So if people want to get there.
Yeah, let me just.
Maybe you can just chat the URL into.
Unfortunately, I can't paste into the chat. So.
Oh, here I can do it.
Okay. Yeah, it's unavailable to me. Yep. Great. So this brings up a welcome page, and you'll see here kind of a file structure on the left. If you open up the notebooks folder, you'll see this 0 demo AWS file. So like I said, I've just launched this a few minutes ago to make sure it runs, but I'll step through. This is sort of a 10-minute demo to demonstrate all these tools that I've just talked about coming together. So our first step here is I'm going to assume people have used Python on this call. So I'm not going to go into a whole lot of detail just because of time. So one option for running these notebooks is you can go up to the file menu on top, and there's a run menu where you can run all cells. So that's one approach to just running everything. Otherwise, you can step through these code blocks one by one by clicking in a code block and running Shift-Enter. So this first section is just searching for data on AWS, and you'll see we're using some libraries called SAT Search. These have been developed by a group called Development Seed. They're very excellent tools for searching these archives on AWS. I'm going to use a bounding box here over Washington State for this search. And so again, these are files that just live in this directory that I've set up in advance. If you look at this, you can open any files over here on the left. So we'll open up this bounding box file, and you can see it's just a JSON file with all the coordinates for a polygon over Washington State. And it's a pretty simple syntax for searching through these archives. In this case, I already know that I want to isolate things based on the path and row of the Landsat data. And I know the name of the collection. I'm going to pass an area of interest and also sort everything by the date time. So this is a Python interface to the searching. And it returns 109 items that are from path 47, row 27, covering this area. The point of this notebook, I should say, as I run through it, is to do this sort of distributed analysis. As a demonstration, I'm just going to use Landsat data over Washington State and calculate NDVI. So this search is using the stack metadata that I mentioned earlier. And everything's done sort of in JSON format. You can save that for later. So you can save your search. You could share this with other people so that they have, a copy of your geometry that you searched with. They also have under features, every Landsat scene that covers this area. I lost audio.
You're back now. I I don't know what's going on.
I suspect it's probably the wireless connection at the university where I'm at.
Okay. Okay. Yeah, I guess that would make sense.
Okay, great. Well, I'm back. Hopefully people can hear this now. I'll just keep running through what I said. Might repeat myself. Sorry if I do. But what we're doing here is using this stack interface to search the data that exists on AWS, and then using some other Python libraries to sort of explore this data set. So pandas is a way to show tabulated data, and so you can kind of browse through and see the scene IDs, the date of acquisition. You also have a amount of metadata like sun azimuth information. Oh, sorry. Go back, etc. I mentioned just briefly in the presentation the PyViz tools, and so that's a collection of Python libraries again that enable sort of a simplified plotting of complex data in Python. So this cell here is plotting plotting this table, which includes data about the geometry, so the footprints of these scenes. And it's quite easy to put this sort of data on interactive maps. So this is using tiled map data just to make sure you're in the right area, make sure your search was effective. All of these plots are interactive, so you can see tools on the right here that allow you to zoom in, for example, on specific regions. All right. Also, as I mentioned, everything is a URL. So it's pretty easy to display any images within this notebook interface. It's just displaying an image in a browser. And this is a simple demonstration of browsing through the thumbnails in your data set. So you can just flip through all 100 of these thumbnails very easily, get a feel for the data that you're about to work with. But ultimately, you want to do some sort of more quantitative analysis. So this cell here is launching a cluster with the Kubernetes system in the background. And we've specified here the number of machines that we're launching. So it's 10 machines. And that will return this cluster interface here. All of these Dask labels on the right are also referencing this interface. So under the manual scaling, you can change the number of machines you have. So if people are launching this now, typically this takes a while to launch, but you can see this number increasing. I just went up to 5. This is reporting the number of cores available to you and the amount of memory available to you. So I recommend, I don't know, 10 to 20 for this sort of an example. And we'll just keep marching through here. This is where we're going to get into a bit of distributed computation. And so these cells here are loading an image with the raster.io library. And we are basically passing a URL to raster.io open, and that Python package is able to read this image file. You can also put it into an Xarray object. So that's where this xr.open raster.io is coming in. And we're printing out down here what that Xarray object is. So if you're running this cell, you can see this returns information to you instantly. And that's because you're just accessing the metadata of this geotiff online. So you're able to access the metadata very efficiently, very fast. If you want to actually pull the data and visualize it, you can use these PyVis tools. So this is the data array Xarray object that we are calling a plot function on. And it may take a second, but what we've done there is we've actually pulled data from this file online. And this, again, is an interactive plot. So what's nice about this PyVis suite of tools is that it can automatically, in the background, account for different resolutions. So this is a 30-meter per pixel data set. And that was fairly quick to pull up this visualization. As you zoom in to specific regions in this interactive view, you'll see the resolution automatically updating. So we're zooming into some fields down here and getting that higher resolution data depending on your zoom level. Another neat aspect of these PyVis tools is that you can do reprojection very easily. So all the Landsat data is in UTM coordinates, but it's very easy to reproject on the fly to different coordinate systems. Like if you want just in latitude, longitude coordinates instead of UTM, you're just specifying what the original coordinate system is, and then the reprojection happens for you in the background. Now you can see as you move around this interactive cursor, we're getting the coordinates in latitude, longitude instead of UTM. Okay, so that's individual images. Now I'm just going to demonstrate a bigger workflow where you're looking at a time series of images. These next cells use the intake package, and intake is really just facilitating right now kind of the loading of the data into a Python object. So instead of this code block up here from earlier, which can get kind of long and specialized in terms of what your, sorry, I've got it highlighted here, of what your commands are to actually get that image into a Python object, in this case, an Xarray data array. Intake allows you to specify how that happens from the catalog to the Python object. So you can look, go back to the cell we were at, on this cell here, get a single image, and you can see we're loading a catalog with intake. And if you open this file, intake Landsat AWS, you can kind of get a feel for what's going on where you're specifying what variables are needed and how the file is loaded into Xarray. This is kind of intended to be behind the scenes and just make it much more easier for a user of that data to load the data in for analysis. So now it becomes just 2 lines of code to read in any image from one of these URLs. Or if it's also specified in that catalog how to load all 8 bands instead of just a single band. So this becomes really convenient, and you can see this all happens very fast because you're just referencing metadata. You're not actually reading any data, but you have this information that for this particular Landsat scene, we've read in 8 bands, all the 30-meter bands, into an Xarray object. So again, we can use these PyVis tools to visualize those bands. Now we're plotting, I'm gonna try and adjust my screen here. All the bands from this image on 2013 July, and it's almost the same command to do the plot, except we've specified that we're going to group by band. That gives you a time slider so you can step through. The sliders can sometimes be hidden depending on how your window's configured, but as you step through these different bands, we're pulling the data behind the scenes and replotting it. So band 5 is NDVI. That one always stands out as being very different. So we've just gone in. Once again, these are all, as I mentioned, interactive. And as you zoom into different features, you get that resolution updating. So it's very useful for exploratory analysis, especially of large imagery data sets. So the final kind of demonstration is loading the entire set of Landsat scenes from this particular path and row. What we're doing here is just in the same catalog, we've specified for NDVI how to load the data. And in this case, we're just going to load band 4 and 5, the red bands and the near infrared band from all the files. So Xarray is pretty neat in some of its functionality for working with these large data sets of imagery, n-dimensional imagery, because it will automatically adjust the dimensions given that all the imagery is in the same projection. So this is all from a single path and row, and we're all in the same UTM zone, but we don't necessarily have the same dimensions on all images. Some may be 10 pixels bigger than others, but you can load these into this Xarray object, and you can see we're working with multidimensional data here. We have a time dimension, 109 acquisitions, 2 bands for this data set. We've loaded the red and the near infrared, and the dimensions for the full resolution 30-meter data. Again, we haven't loaded anything into memory, but this full data set size is about 100 gigabytes. So it's more than you would want to deal with on your own laptop. And I'll just launch this final kind of demonstration of interactive visualization down here. One thing to notice, what I'm doing in this cell is just creating a different Xarray object, which is referred to as a data set. And we're pulling out the band information that was in a dimension and assigning it to a data variable. And that just allows us for more convenient referencing of what we're working with. You can also see down here, for each data variable, you see a chunk size listed. And that is what Dask is using to farm out any computations on this array to the distributed cluster that you have. So Dask is going to take, of these full resolution images, tiles, in this case, per timestamp, so that's going to be on an individual date. We're going to send out 1600 by 2000 pixels as an individual computation to be run in parallel. You can change these chunk sizes if you want, depending on if your arrays are float valued or integer valued. You may want to change these chunk sizes so that they're an appropriate amount of information that you're sending to each machine. So that's what's happening here. And finally, we'll just do a NDVI calculation. So this cell here is this NDVI index, and we got something back instantaneously, and that's because all of the interactions with Dask are what are called lazy computations. And so we compute a graph of how that value is actually going to be computed, but we don't compute it until you issue a command to compute or you try and visualize the result. So once we run this cell, again using HoloView's plot, the cluster is going to fire up and start sending those chunks out to our distributed machines, and then ultimately pull back the result. So that's what we're getting right here. Again, we've used this group by time. So this is the NDVI calculated per scene. And you can march through this data set again with the time slider. You can also zoom in and kind of query these values in any particular region. A little bit slow for me here. You can also extract the time series. So for any particular point, you can click on this map. You should get a little white dot. So you can select different points and compute a time series based on those points. So I'll run these next cells, but I'm kind of going to wrap it up here. These can take a little while to compute because you're marching through a lot of data out there. In this case, it's 100 plus gigabytes of data that you're churning through to generate many of these plots. So it's not necessarily instantaneous, but it's fairly quick and something that just simply can't be done on your laptop.
Hey, Scott, can I ask you, did you learn all that stuff about PyVis by, say, going through the PyVis tutorials, or, how did you figure out how to do all that? What was the best resource for you?
They have some very good documentation. These are kind of software tools that are constantly in development. So it just takes, I think, a bit of exploration of whatever documentation is out there, demonstrations, and their examples.
Okay.
Yeah. So yeah, there's definitely a learning curve to all of these tools, and that's part of the reason we're putting a lot of emphasis on these demos that people can launch from this binder interface. And I'll just by going back to this presentation where we have a list now of quite a few demos that I encourage people to check out and spend some time going through. And I want to end with these conclusions. A lot of potential to get the most out of the remote sensing data sets as things move to cloud storage. It's opening up a lot of opportunities for people who want to answer questions that have like a regional scope that you simply can't address with limited computational resources. So I think right now there are a lot of opportunities to get involved in this project, in particular if you have scientific use cases that you'd like to explore using some of the tools I've shown here. And it's really more than what we have just showcased here. It's a community-based effort. So there's a great website documenting what's happening with this project, and all the communication is mostly happening on this GitHub page through issues. So you can read through what people are currently interested in working on, and it's very easy to chime in there. Finally, I'll just pitch some of the projects we have going on here at University of Washington. There's a big educational component to this project. A lot of these tools are not intuitive or familiar to people, especially folks who may have backgrounds using software tools on a desktop. MATLAB, for example, doesn't translate well to what I've discussed here today. And we're putting on these week-long Hackweeks that have an educational focus here at the University of Washington. And many of these are geoscience focused. So there's one coming up in September that I encourage people to look into if you'd like to learn more about this stuff. Also, we've put together even these week-long sessions targeted really at specific sensors and satellites. So there's an entire week dedicated to working with ISAT-2 data that's coming online here very shortly. So yeah, thanks everyone who called in. I'm happy to stick around for a bit and answer questions that you might have.
Yeah, I'm happy to stick around for a while too. I know some people are going to drop off, but this is a great chance to ask Scott. That was fantastic. That was an incredible tour de force of a lot of technology, and if that didn't get people excited, I don't know what will. But so that's thank you so much for that. That was really clear. And as you said, those notebooks are going to be super useful. I know I'm going to go and look at a few of those things that you did because I could immediately use that in my own workflows. So I'm going to open this up. I'm going to unmute everybody. Who wants to ask a question? Scott, a question.
Hey, Scott, this is James Gallagher from OpenDAP. Hey, I was wondering a couple things. Can you make some more of those links available? It was really great that you pasted the one in the chat window, but I noticed that that it wouldn't let me do the parallel run while you were using it too. So it'd be cool to be able to go through it a bit more. But also, have you looked at using range gets with the HDF5 files? And would you be interested in doing that?
Yeah, it's not something I've looked into. I was under the impression that it required software on top of the HDF library to do that. But certainly, we're not tied to any particular format right now. We're just looking for formats that do enable the range gets, but we're really focused only on freely available tools. So as long as it's a free software, happy to explore it.
Sure. So yeah, okay. Well, maybe we could talk about that then.
Mm-hmm. Sounds good. At the so at the top of the chat, there's a link to this presentation, and all the demos that we've got put together to date are listed on this slide and part of the presentation in the Google slides. So if anyone's wanting to explore some different demos, I would point you to these links.
And I can add that link, or Dave can add that link to the Tech Dive page where we're going to have the link to the recording of this, so that other folks could easily get in there without having to dive into the presentation and then go there.
Sure, that sounds good. Yeah, unfortunately, I don't have access to the chat box, so I can't paste anything.
Yeah, that's bizarre. We'll get that figured out for next time. I'm sorry. Occasionally there's a new feature, which is also a bug, of course. So that's great. I just wanted to also point out that one of the cool things that if you went back up into your notebook, you'd probably see that you got all the processors now that you asked for. The processors can come and go with Dask, which is pretty cool. So if you get new ones, as you're running your workflow, it doesn't matter. And if some drop off, it also doesn't matter.
Right. I got a question. This is Joseph Kellendorfer. Scott, great presentation, thanks. How do we use the notebooks in a offline approach? In other words, if I wanted to execute a workflow to get to an NDVI, as you've shown, for example, but want to do that globally on all the data, whatever available, so I certainly don't want to sit in front of a notebook. How would that be done?
So the interface we're really advocating for is this Jupyter interface. You can still run and execute scripts from that interface if you want it to be a bit more automated. offline is tricky because a lot of the functionality we're demonstrating here is predicated on the fact that you're running next to this cloud storage. That said, there are demos. We have a system deployed on NCAR's Cheyenne HPC system. So there are demos using running this sort of interface locally, I guess, offline in that sense, and running against the data that's on the NCAR computer. So the key is that you would want to run it wherever you have the data set. And as long as you had a Landsat archive that was local, then you could run this locally the same way I'm demonstrating.
No, sorry, I think that wasn't quite my question. I didn't mean offline in terms of not close to the data, but if I wanted to execute a huge workflow and process all the Landsat data to an NDVI, but I don't want to certainly sit in front of or have my computer up and running to have the notebook executed. I want to essentially close the laptop, go away for days or whatever, how long it takes, and then come back to the results. How would that work with?
Yeah, that's a good question. It's something we're currently working on. So basically, it's submitting a batch computational flow that will run in the background, right from the notebook. You could do that.
Okay, so that's in development. That will help us in the future. Yeah.
I think we've lost Scott's audio again. He's probably saying more about that.
Yeah.
Yeah, I mean, you can. I don't know if he was going to say. I mean, you can certainly save these as regular Python. You know, you can save the notebook as regular Python and execute that code, you know, from the Jupyter Lab interface. But you could do it without keeping that open, I think.
Yeah, is that the approach to do it?
I'm not sure what Scott was going to say. Yeah, actually, he probably doesn't realize we can't hear his audio, or maybe he can't hear
us either. Yeah.
Yeah. All right. Well.
Yeah. Okay.
Sorry, I think the audio connection keeps dropping out for me.
Yeah. So you were going to. So Joseph asked about, you know, the batch. I said that you could, you know, you could of course save your notebook as a regular Python file and run that, but I think you might have been saying something else, but we couldn't hear you.
Yeah, so I was just pointing out that this kind of scalable cluster behind the scenes that can be tailored depending on your flow. So if you did want to look at the entire global data set, you could launch many more workers and not wait many days for a computation like that to compute. But it's not something we've really set up demonstrations of yet, but it's certainly possible.
Yeah, I mean, right. I just am curious how to use this in a batch mode, essentially. Walk away from it.
So Scott, are you saying instead of, you know, you could just launch 2,000, you could have 2,000 CPUs or something working instead of, you know, 10 or whatever?
That's
right. Yep. As one option. The other thing is,
yeah, sure. It still doesn't necessarily get us there. I mean, it still might take a long time, also depending on the throughput and where the data sources are. I just think we need an offline. I mean, a batch mode that doesn't require running it interactively, no matter how many workers you fire up.
Yep, that's a fair point. Yeah, a lot of the demos we've been showing are focused on kind of like the interactive post-processing stage of an analysis, where it's once that batch flow has run and you're working with products.
I mean, it's super neat with all the visualization, etc. No question. If I may, there's one other question I had, and that's back to the discussion of HDF or NetCDF and cloud optimized GeoTIFFs. Any experience with using the flexibility on cloud optimized GeoTIFFs with virtual raster tables in mixing and matching and time series building, and how those interact with the cloud store?
A bit, yeah. So I've been kind of trying to go back again. I've been exploring that a bit myself with some of my own work. You can kind of see in some of these other demos. Sorry, slides keep changing. There we go. There's some demonstration of that in this fourth demo using stack catalogs, mosaics.
Okay.
The demonstration of creating a VRT file that you referred to as a means to start like compositing and mosaicing data. I think it's certainly something we're interested in, but we haven't really figured that out yet.
Yeah, that may be something we should talk more, because I've worked with that quite a bit, and it seems to be quite flexible and powerful as well.
Mm-hmm.
And in the whole discussion on how we approach it and store it, I get a lot of feedback on GeoTIFFs being a very liked product in the applications communities, etc. So
Mm-hmm.
as we prepare for the NISAR mission, for example, we're going through this discussion.
Joseph, you're on the NISAR planning team or something?
I'm on the NISAR science team, yes.
Okay.
Yeah, no, it'd be great to talk more about
Yeah.
NISAR in particular.
Great. Yeah, excellent. Thanks, Scott.
No, you're welcome.
I have a final quick question. This is Hamed from Radiant. Thanks, Scott, for the nice presentation. My question is that the Access project and the grant you mentioned. So the Jupyter Hub that you will deploy as part of that, you mentioned it will be for community use. How NASA is going to manage that? I mean, it's not open to everyone, right?
Yeah, that's true. Maybe I should have been a little more careful with the community use. But we're trying to get people involved. In my experience, there's not going to be 100,000 people immediately kind of diving into use this. It's a kind of a community that already has some level of interest or a scientific question they're looking into and ask to try and use it. So we're sort of going with the whitelist system, and that's the extent of our community use so far. That said, the Binder demos are being paid by grant funds currently, and so the longevity of the project is certainly something that we talk about a fair amount, but we don't necessarily have a clear vision for how things will be supported in the long term. These tutorials currently are mainly supported by two grants, one coming from NSF and another coming from NASA. But we've also been provided cloud credits from Google Cloud and AWS to prototype this stuff. And so it's basically all running on credits for now.
Okay, good. Thank you.
All right. Well, thanks again, Scott. That was fantastic. And I look for the ESIP Tech Dive page to show up a recording link if you want to share this with any of your colleagues. So we'll see you next month. Thanks, everyone.
Yeah. Thanks, Rich.
Thanks.